Welcome to our session about second quantization, mean field, and spontaneous symmetry breaking. Today, we are going to focus on a technique that allows us to understand how quantum mechanics can actually appear at macroscopic scales in a very specific type of materials called quantum materials. And in particular, we are first going to understand what a quantum material is, which kinds of different quantum materials there are, and how we can rationalize their properties using this formalism. We will see how we can use quantum mechanics and how we need quantum mechanics to understand quantum materials, and in particular, how second quantization is a very important tool to rationalize all these properties. We will, of course, understand the basics of second quantization, how it is related to first quantization, and how we can use it to account for systems that are both free particle systems and systems with many-body interactions. And in particular, in the case of many-body interactions, we will look at a technique called mean field theory and use it to understand something called spontaneous symmetry breaking, which is the development of specific orders driven by quantum many-body interactions. It is useful to start thinking about how quantum materials came to our attention, and in particular, how quantum materials have become one of the most important pieces that build our future technologies. And if you think from a historical perspective, humankind has always relied on materials to develop technology. If we look back very long ago, we were in the Stone Age where most of our tools were just based on stone, and for that time they were good enough. Then afterwards we moved to the Copper Age where most of our tools were made of copper, and that allows us to do things that we were not capable of doing with the previous stone tools. Then just a few decades ago we were in the Silicon Age that effectively drove this whole revolution in the information era, and that you are currently using just to see this recording. And if we think ahead, if we think about what comes next in the next few decades and even in the next few centuries, then we would find ourselves in the quantum age, the age in which our technology strongly relies on quantum properties of nature, and in particular, where our technology relies on being able to harness quantumness at microscopic scales. And so understanding quantum materials is, in a way, one of the steps that we need to make in order to go towards this future direction, to the direction where we use quantumness as one of the resources for our technology. And in particular, quantum materials are the platform that allows us to harness this quantumness, and in particular, to realize quantum matter. And so if you just think about past impacts of quantum materials, you can already find many in a variety of different areas. So in particular in medicine, if you think about MRI techniques, then they rely on superconductors, which are one of the first quantum materials that were discovered. These are materials that can have an electrical current without any sort of heating, and that of course they in principle appear only at very low temperatures, but they are an extremely important tool for nuclear magnetic resonance, of course, because they allow you to create very, very large magnetic fields. If we think in terms of renewable energies, solar cells are a very specific type of quantum material that rely on semiconducting physics. And in particular, these types of materials are essential for our future energy energy technologies. And then if we think ahead and we think about what would be the future of computing, then we would have quantum computing. And of course, quantum computers, they strongly rely on a variety of quantum materials, including superconductors, semiconductors, magnets, and many others. So quantum materials are a fascinating area from the fundamental point of view. They are one of the central areas in quantum technologies, but they also have an exceptional importance for applications. They already have, and in the future, we hope that they will have even more. And if we think about this in a much broader sense, quantum materials actually are one of the key directions to tackle some of the most important challenges that we have in the world. And in particular, if we think in terms of the sustainable development goals, quantum materials actually go in several of the directions and help us support the mission of several of these sustainable development goals. And in particular, there are five that are very important, and that of course quantum materials have a very direct impact. So number 9, which is industry, innovation, and infrastructure, and 8, which is decent work and economic growth. These two directions can benefit strongly from quantum computing, as quantum computing creates a whole new industry based on quantum materials. We need quantum materials to create quantum computers. We can use quantum computers to design new quantum materials. And of course, all these quantum computers and quantum materials can have a much wider impact in many other different areas, including biology, medicine, chemistry, and so forth. And then if we focus on the Sustainable Development Goals number 13 and number 7, climate action and affordable and clean energy, quantum materials also have a central role, which is in the case of solar energy. Quantum materials allow us to harness all this energy coming from the sun, and we think in terms of having lower consumption electronics based on, for example, superconducting electronics or topological insulators that would drastically reduce the energy consumption, then quantum materials would also support this mission. And if we think in terms of the Sustainable Development Goal number 17, partnership for the goals, the development of quantum materials and in general quantum technologies often requires a wide international collaboration between physicists, chemists, material scientists, mathematicians, and so forth, both on the theory side and on the experimental side. And this development, this challenge of developing quantum materials is, of course, something that can bring the world together towards a inspiring and challenging goal. So if we think about very specific types of quantum material that we will try to understand during this course, we will have two very specific examples. So we have the case of semiconductors for renewable energies. Semiconductors are perhaps one of the easiest materials to understand in a sense that they can be understood from the point of view of single particle physics. And this is a type of material that you have already seen in basics of materials physics. And for quantum computing, however, we actually have materials that are more sophisticated, and sophisticated in the sense that they need a more challenging formalism to account for their properties. So, for example, if we think about two different platforms for quantum computing, superconductors, for example, superconductivity relies on many-body interactions between electrons, and these many-body interactions create a macroscopically coherent state that is based on Cooper pairs, that is based on condensation of Cooper pairs. And to understand this type of state, we actually need to rationalize many-body interactions and to use second quantization. And if you think about, for example, other platforms for quantum computing, such as, let's say, topological quantum computation based on superconductors and semiconductors, then for those types of quantum computing platforms, we also need second quantization, and we also need to understand the effect of quantum many-body interactions. There's a very inspiring summary of what has been the impact of quantum materials, both in the past and what we can expect in the future by the American Physical Society. So once you have some time, I would strongly encourage you to watch this recording that provides a very fantastic overview of different types of quantum material that we find in nature, what are the challenges to understand these materials, and many other crucial questions. Okay, so in order to have an overview of what we are going to understand during this course, let me show you a variety of different types of quantum material that we will be able to rationalize. So one of the simplest types of quantum materials are insulators, which are systems where electrons effectively they cannot propagate. And they cannot propagate just because the bond structure does not allow them to move in space due to the existence of a finite band gap. There's a wide variety of insulators. Magnesium oxide is one of the most common ones, but of course, sodium chloride, just basic salt, is another conventional insulator. Boron nitride in the two-dimensional world is another type of insulator, and so forth. Although insulators seem like a relatively simple type of material, it is worth mentioning that there's a very specific class of insulators that are called topological insulators that have exceptionally non-trivial properties. So when you look at the bulk in both conventional insulators and topological insulators, you seem to see roughly the same. There's a finite band gap, electrons cannot propagate, but then once you look at transport properties and once you look at the edge, then these two materials are completely different. And to understand this difference between conventional insulators and topological insulators, we need some of the tools that we are going to discuss during the course. Another type of material, of quantum material that we are going to study is the case of semiconductors. And there's a wide variety of semiconductors. We have gallium nitride, for example, silicon, has been an exceptionally important part of our electronic technologies, have gallium arsenide and many others. The formalism to describe semiconductors is very similar to the one that we need to describe insulators. Both semiconductors and insulators are systems that are effectively accounted for by single particle physics, meaning that in principle we do not necessarily need to have a formalism that includes electron-electron interactions. Electrons move as if they are independent, and the most important thing to keep in mind is Pauli exclusion principle, but apart from that, then we can use a single particle picture. Semiconductors are different from insulators in the sense that the electrons can move because they are slightly doped. So they have effectively free carriers, and these free carriers are the ones that are responsible for doing logic in electronics, for harnessing energy in solar cells, and so forth. A next type of quantum material is magnets, and in particular for magnets, antiferromagnets, spin spirals, and so forth. These types of materials, they are already correlated materials. So magnets only exist because electrons interact with each other. Magnets only exist because electrons are expelling each other due to Coulomb interaction. And this Coulomb interaction sometimes gives rise to ferromagnetism, meaning that all the electrons point in the same direction in the material. Sometimes it gives rise to antiferromagnetism, meaning that in different sides of the system, electrons point in opposite directions, or sometimes they give rise to spin spirals. Electrons effectively point in a direction that changes in space, but in a very ordered way. There's another type of magnet that it's not ferromagnet, antiferromagnet, or spin spiral, but that they are quantum magnets. These are systems that have locally a local magnetic moment, but all these local magnetic moments are entangled. There's an entanglement at the macroscopic scale in these materials, and in particular, you effectively have a magnet that when you look at it macroscopically, there's no magnetization whatsoever, and all the sides form singlets with each other. This, in a way, is one of the most fascinating types of quantum materials, and it's also one of the most challenging ones, but we are going to discuss them more in detail in the next few sessions. There's a whole type of quantum materials that are topological insulators that we mentioned before. And in particular, the most well-known type of topological matter is the so-called Dirac semimetals, which is the case of graphene. Graphene is simply a honeycomb lattice of carbon atoms. It's just one layer of graphite. And this relatively simple structure has exceptional electronic properties. Electrons have a protection when they propagate due to a topological property, due to a Berry phase. Graphene is also one of the building blocks to create other types of correlated states and other types of topological phases. And there's a whole class of topological states that show very similar properties to graphene. We have quantum spin Hall insulators that are systems that show a gap in the bulk, but then helical states at the edges. We have churn insulators, which are systems that show a gap in the bulk, but then chiral states at the edges. We have, let's say, chiral superconductors that are superconducting systems that show propagating Majorana excitations, crystalline topological insulators, and many others. All these states can be accounted for by using single particle physics, and all those properties are a simple consequence of single particle phenomena and a non-trivial mathematical structure of the single particle Hamiltonian. This is, of course, something for which we are going to dedicate a whole session. One of the most popular types of quantum materials are superconductors, and superconductors can have many different families. There are conventional superconductors like aluminum, for example. These types of materials are effectively driven by phonon interaction. So electrons emit phonons. These phonons interact with other electrons, and this coupling of different electrons through phonons essentially creates Cooper pairs, and that gives rise to the superconducting state. But then there's a whole new family of superconductors that are called correlated superconductors, such as cuprates, nictates, and so forth. And those systems are way more challenging to understand. Superconductivity, and in particular correlated superconductivity, is one of the biggest open challenges in science. And we currently don't have good enough tools to predict correlated superconductors, and correlated superconductivity is one of the hardest problems from a theoretical standpoint. So this is one of the directions that we are going to discuss very much in detail in the next few sections. And what is very important to mention is that superconductors, both conventional and correlated superconductors, are an exceptionally important building block of many types of quantum technologies, both quantum computers, quantum detectors, and many others. Perhaps the most exotic type of quantum material is what it's called fractional quantum materials. These are quantum materials where the fundamental excitations are no longer electrons, but they are fractions of electrons. So you can think about materials where electrons kind of split into three different parts. You may have one part that when you bring together with other two parts creates a full electron. And even though this sounds like incredibly artificial and incredibly challenging to understand, there are very well-known cases where this happens. And one of the most well understood cases is the case of fractional quantum Hall states that have been observed already for many decades, in particular in gallium arsenide. Fractional quantum matter is also one of the most important directions recently because there have been experiments that show how we can get fractional quantum matter in much easier ways than what we thought before. And fractional quantum matter, in particular fractional Chern insulators, can be building blocks for whole new types of quantum devices and quantum computers that before we didn't even consider that we would be able to do. Okay, so we have been discussing about different types of quantum materials. Of course, all these quantum materials are made of the same building blocks in a way. So all materials are made of electrons, protons, neutrons, and photons, and that's all. And somehow, when we combine these four elements in different ways, we get all this widely different phenomenology. In particular, for us, most of the phenomena of quantum materials can be understood just by motion of electrons and motion of electrons that interact in a certain way, and this interaction is mediated by, let's say, nuclei that is formed by protons or neutrons or by photons through the Coulomb interaction. But in practice, for us, we are going to mainly focus on interactions between electrons, interactions mediated by effective interactions. And those interactions, just depending on how your original electronic structure was and the details of the interaction, can give rise to a whole variety of different behavior. So you can think that maybe the simplest type of emergent behavior is vibrations of the lattice, vibrations of the nuclei of your material. This is a type of quasi-particle that it's called phonons, that it's maybe one of the easiest quasi-particles to understand. It also exists classically. You don't need any, let's say, quantum mechanical treatment of the material to understand that phonons exist. Then another more sophisticated type of excitation or quasi-particle that appears quantum materials are magnons, and they appear especially in systems that have magnetic order. So if you think about a ferromagnet, in a ferromagnet, the magnetic moment points in the same direction all the time, and you can think that if you put a little bit of energy into your system, this magnetic moment can vibrate a little bit, and when it vibrates, it effectively allows you to, let's say, transport energy from point A to point B. This transport of energy is what it's called a magnon, and it has a finite spin, and in particular spin 1. Something that is very interesting is that magnons can appear in systems that are insulating. So you can have a system that is an insulator due to electron-electron correlations, such as a multi-insulator, and even though the system cannot transmit charge, it can transmit spin due to the fluctuations of the magnetic moment. Before, we discussed that some magnets show quantum entanglement at macroscopic scale, and some magnets effectively don't break time reversal symmetry. In those magnets, we can have a completely different type of excitation that is called spin-on. And spin-on is a spin 1/2 excitation, but that doesn't have charge. So you can think that a spin-on is only the spin sector of an electron. The charge is frozen, but the spin is free. And spin-ons are one of the simplest cases of fractionalization of the electron, and more generically of something called spin-charge separation. Then, even without considering many-body interactions, if we look at topological materials, we can actually have Dirac fermions. So we can have electrons where the equations of motion follow the Dirac equation instead of the Schrodinger equation. So electrons behave as if they were massless, and they have a linear dispersive relation, meaning that the momentum and the energy are proportional to each other. This is something that in principle is not expected because electrons are expected to behave following a Schrodinger equation, but if we have the right geometry and the right Hamiltonian, then we can have Dirac fermions. And this is something that appears in graphene, for example, in the honeycomb lattice of carbon atoms, and it is one of the reasons of the exceptional properties that graphene has. And then if you think about some more complex states, such as, for example, superconductors, in superconductors, the order parameter, or what allows us to know that a superconductor is superconducting, is something called the pairing of the system. And the pairing is characterized by a phase that goes between 0 and 2 pi. A vortex in the phase can appear in a superconductor. In particular, is one of the most important features that allows us to use superconductors to, for example, let's say, measure the charge of the electron and then Planck's constant and so forth. And vortices, they are quasi-particles in a way. They have their own dynamics and they can propagate in space. So in a way, they are also an emergent property of electrons. Okay, so we have discussed that there's a wide variety of phenomena that can appear in quantum material just by the motion of electrons. But one of the most important questions is how can we go from individual building blocks that are the atoms to a crystal, to our quantum material, and understand how the property appears. How do we go from individual blocks that we understand relatively well? So individual atoms are relatively easy objects, and they don't show fractionalization, then they don't show vortices, they don't show magnons, they don't show spin-ons, but somehow when we put them together in a lattice, all these behaviors arise. This course is focused on doing this step, going from atoms to quantum materials and understanding this quantum behavior. Okay, so let us start from the beginning. We are going to deal with a quantum mechanical system, and a quantum mechanical system is effectively described by a Schrodinger equation. So we effectively have something that we call a Hamiltonian. This is a matrix in a way. Then the state of the system is described by a wave function. This can be a single particle wave function or a many-body wave function. It doesn't matter here. And then when we apply the Hamiltonian to our wave function, this effectively tells us how the wave function is going to evolve in time. So if we integrate this differential equation, we can effectively predict what the wave function of the system is going to be at any time if we know the wave function of the system at time equal to 0 and the Hamiltonian of the system. This is general. This allows you to deal both with single particle systems and with quantum many-body systems. Of course, the challenge is that for quantum many-body systems, solving this equation is exceptionally hard. So for our discussion, we are going to discuss separately single particle systems and many-body systems. And in practice, for single particle systems, we can solve this equation exactly in every practical case, whereas for many body systems, solving this equation becomes exceptionally hard very, very quickly, and in general, we cannot solve it. Of course, much of the topology quantum matter that we are interested in relies on quantum many-body interactions. So we somehow need some technique capable of dealing with these many-body Hamiltonians. And this is, of course, something that we are going to discuss. These techniques are approximate, but even though they are approximate, they effectively allows us to rationalize and understand much of what is happening in quantum materials. Okay, so let us think about these two different situations. So in single particle systems, we can effectively consider each electron independent. And in particular, if each electron is independent, we can just think about what is the motion of individual electrons. And by understanding the motion of individual electrons, we will effectively understand the motion of any possible combination of particles. So for these systems that are single particle systems, we can use something that is called first quantization that effectively relies on describing the wave function of the system for a single particle and predicting what is the dynamics of this single particle wave function. And for this, we usually work with something called the Hilbert space. This kind of technique that you are familiar with from quantum mechanics is capable of dealing with a wide variety of systems. You can describe metals with this formalism, semiconductors, insulators, even topological insulators. And it is fair to say that it's one of the most successful, easy formalisms that allow you to account for much of the phenomena that we observe in conventional solid state systems and some of the quantum materials. However, there are some quantum materials for which we cannot use this formalism. There are some quantum materials where electrons are not independent, and even more generally, there are some quantum materials where the number of electrons fluctuate, meaning that at some time you have one electron, then you have two electrons, then you have three electrons, then you have four electrons. So if that is the case, if your number of particles is constantly fluctuating in time, you cannot write down a wave function for a fixed number of electrons, but somehow you need to deal with a system that has a fluctuating number of electrons, and you need a formalism that can deal with a system that has a non-constant number of electrons. And for this, we have second quantization, which effectively it doesn't focus so much on how many electrons our system has, but it rather focuses on how electrons go in and out of the system and describes the dynamics of this creation and annihilation of electrons. This type of formalism is incredibly important to describe superconductors, superfluids, different types of correlated materials, and so forth. And in particular, it allows you to predict much more exotic phenomena. For example, the existence of spin-ons, fractionalized electrons is much easier to do with second quantization, but all these problems are, of course, much more challenging. And in general, when you have a system that requires you using second quantization, which in practice means that you have strong many-body interactions, then getting exact results is much more challenging, but it is also much more exciting. Okay, let us start first with a relatively simple single particle system. So if you think, for example, about a lattice of sites, so a lattice of individual sites that have a single level, a single electron, and they form a specific island, for example. If you don't have quantum many-body interactions, the only thing that you have is a single particle problem. And any single particle problem can be diagonalized. So you can find some diagonal bases where the eigenenergies can be computed and the eigenenergies can be sorted out from the smallest one to the biggest one. So this is the typical problem of, for example, particle in a box. So you have the lowest energy state, the first excited state, the next excited state, and so forth. And this is, for example, what happens in a quantum dot. So if you take a nanometer size semiconductor, then effectively you can ignore electron-electron interactions and you can think about what are the single particle states in this quantum dot, and you get all those states that you observe here. If you're thinking in terms of single particle physics, you can say that the first level or the lowest lying level is state number 0, and the first excited state is state number 1. So having one electron in E0 is state number 0, having one electron in state number 1 is this other state. And these are single particle states, meaning that you are either in 0 or in 1 or in a linear combination of both. But regardless of which situation is the one that you have, you always have one electron in the full system. So now the question is, let's imagine that we want to describe a quantum dot where the quantum dot sometimes has 0 electrons and sometimes it has 2 electrons. And we have a coherent superposition of these two states. So we have 50% probability of having 0 electrons, 50% of having 2 electrons, and this is completely coherent. Of course, for this situation, we can no longer write a simple wave function because the wave function needs to have a certain number of coordinates, and you cannot have 0 and 2 coordinates at the same time. So the question is, how do we describe these types of systems? This is, of course, something that appears in many different instances, not only when you consider a quantum dot that has a fluctuating number of electrons, but for example, just when you consider electrons interacting in magnets, so electrons interacting in systems that have local magnetic order, you can use this notion of fluctuating number of electrons to understand how the different magnetic moments couple to each other. And this is exceptionally important, for example, to understand the ferromagnetism and antiferromagnetism of a variety of oxides and give rise to something that is called the Goodenough-Kanamori rules, that are the rules that allow you to predict which systems are going to be ferromagnetic, antiferromagnetic, and so forth. And for this, you need to use this notion of fluctuating electrons. And more in general, there are quantum materials where the mathematical description that you have intrinsically has a fluctuating number of electrons. And in particular, in a superconductor, the order parameter that we have actually breaks the conservation of electrons, meaning that just saying that you have a superconductor implies that you are assuming that the number of electrons is not constant. The parity is conserved, meaning that you are in a quantum superposition of 2, 4, 6, 8, or 3, 5, 7, so forth, but you do not have a precise number of electrons. Okay, so how do we deal with these different situations where we don't want to force that we have a fixed number of electrons? So for this, we describe or we define two different types of operators, which are called the annihilation and creation operators. The annihilation operator effectively destroys one electron in site I, and the creation operator creates an electron in site I. These two operators are, let's just say, matrices. So now we are going to write our Hamiltonian in terms of these operators, and all the dynamics of the system is going to be written in terms of these operators, in terms of the annihilation and creation of electrons. Of course, when we compute expectation values, when we compute observables, we always need a specific number, and the way we get a number is by combining these operators with specific vectors, and the vectors that we are going to use are the empty state and the many-body grounded state of the system. And in particular, we can start by defining the empty state as the state that has no electrons whatsoever, meaning that when we destroy an electron in the empty state, we get 0, like the actual number 0. And so in terms of the dynamics of the system, we are going to use these annihilation creation operators to write the dynamics. So if you think about, let's say, two atoms that are close to each other where electrons can jump from one to one another, you could write this Hamiltonian. So if an electron can jump from site number 1 to site number 0, you would say, well, an electron can get destroyed in site number 1 and then appear in site number 0, and vice versa. So this type of term is what it's called a hopping. Is a term that essentially tells you that electrons from level 1 can go to level 0 and vice versa. So with this second quantization formalism, we can describe all the possible different states that a two-side system can have. We start with the empty state, and the empty state is, as we mentioned before, the state that has no electrons whatsoever. So we say that there's no electron inside number 0, no electron inside number 1. Then our state that had one electron inside number 0 is defined as creation operator inside number 0 times the empty state. So now we have an electron inside number 0. The state that had one electron inside number 1 is now creation operator inside number 1 times the empty state. So now we have our particle in level 1. And now if we want to have a particle in level 0 and a particle in level 1, we just create a particle in level 1 and we create a particle in level 0 and we end up with this state. So with this idea of creation and annihilation operators, we can effectively have these combinations of no electrons and finite number of electrons. Okay, so far we have been talking about electrons, and electrons are fermions, but we have not enforced at any point any notion of fermion. And in particular, we have not distinguished these operators from these operators for bosons. And the idea that so far everything that we described can be applied to either fermions or bosons. So the question is, how do we distinguish between them in terms of these operators? Well, the distinction between fermions and bosons come from the algebraic relations between the creation and annihilation operators. And from conventional quantum mechanics, we know that if we have fermions, then our quantum particles need to follow Fermi-Dirac statistics, which in practice, it means that if we switch the coordinates of two electrons or two fermions, then we need to pick a minus sign in the wave function. And as a simple consequence of this, then you can have either 0 or 1 fermion per level, but you cannot have two fermions in the same level. You can enforce these mathematical properties directly by saying that the creation and annihilation operators have anti-commutation relations. What this actually means is that if you compute C dagger C, C, C dagger, you get a delta function, and the anti-commutation is effectively 0. So this property over here automatically implies that you cannot have two particles in the same level, because if I and j are the same, then the square is 0. And you also get that the wave function is antisymmetric, which is what you were expecting from the, let's say, Pauli exclusion principle. Okay, so to summarize, second quantization is one way that allows us to write Hamiltonians and account simultaneously for states that can have a one electron or a fluctuating number of electrons. From, let's say, conventional quantum mechanics, you were probably using first quantization, and in first quantization, and in particular in a tie-binding basis, one would usually write a Hamiltonian like this. So you have hopping amplitudes. This is state number I, this is state j, and the hopping is written in this way. So what this actually means is that if you are in site number j, you can actually jump to site number I, and with this probability with this hopping amplitude. This Hamiltonian in first quantization can be directly translated to this Hamiltonian in second quantization, and the t's are exactly the same. Then when you take this Hamiltonian first quantization and diagonalize it, you get your eigenenergies epsilon a, and you can do the very same diagonalization using second quantization and get the eigenenergies epsilon alpha. And of course, the way you diagonalize this Hamiltonian in first quantization is by doing a unitary transformation on the local orbitals to the diagonal basis through a unitary transformation U, and you can use the very same unitary transformation in second quantization. Something that is important to note is that this ket psi here is a vector, whereas psi here is an operator, but everything else remains the same. So for single particle systems, or for systems that don't have quantum many-body interactions, when you go from first quantization to second quantization, you nearly don't have to change anything. All the mathematical transformations work in the same way, and systems are equally easy to solve using first quantization or second quantization. The main difference comes when you actually have quantum many-body interactions. And so let us look at this specific case. Let's say take a relatively simple Hamiltonian. So let's take a Hamiltonian of three sides. And when we have three sides, we just have to consider three different levels. But now, instead of just having a single particle term, that it's this one over here, we are going to add quantum many-body interactions. And these quantum many-body interactions are in particular terms that are biquadratic in the field operators, and in particular biquadratic in the fermionic operators. What this actually means is that you can no longer just deal with states that have one particle, but you need to consider the full Fock space. You need to consider states that have one particle, two particles, three particles, and no particles, and so forth. And in particular, if you think about a system that only has three sides, then the total number of levels that you have is 8. So you have the state that has no electron whatsoever, then three states that have an electron in the first, second, and third level, then states that have two electrons in the first and second, first and third, second and third, and then finally the state that has electrons in all the levels. This is for three sides. If you keep doing this for bigger and bigger systems, and in particular for systems with L sides, what you actually see is that when you have quantum many-body interactions, you in general need to deal with a system that has 2 to the L elements. So we have to consider 2 to the L basis vectors, whereas if you only focus on single particle state, then you have L sides. So in practice, if you have a system with L sides, if you can use the single particle states, then you just need to solve a L times L matrix. Whereas if you have to deal with all the many-body states, you need to solve a 2 to the L times 2 to the L matrix. And that is the reason why a quantum many-body problem is much easier than a single particle problem. And so if you think in terms of the wave function of the system, in a many-body system, you would actually need to describe an exponentially large number of coefficients. So if you think about a quantum many-body problem that has L sides, then the wave function would be written in this way, with Cn1 and 2, all the different coefficients that you need to consider. And since you have L sides, there are 2 to the L coefficients, and therefore, to get this wave function, you would need to diagonalize a 2 to the L times 2 to the L matrix. This becomes nearly impossible to do once you are above L equal to 20. And 20 sides is a relatively small number of sides, and that is why the quantum many-body problem is so challenging. This type of problem of exponential increase of the system size is something that appears in general for many different quantum particles. The most important cases that we are going to consider in the course are spinful fermions, where we can actually have two different types of fermions per site. So electrons have a spin. So in a same single particle level, you can have up or down. So in total, there are 4 different states for each atom or for each orbital. Then you can have spinless fermions if you forget about the spin. And this is, for example, what happens if you can consider a single spin flavor in a material, either because your system is ferromagnetic or because you have a very large magnetic field. And of course, you can also have quantum particles that have spin and no charge. And in those cases, the increase of the Hilbert space is still exponentially fast, but then the commutation relations are actually different. And those are spin sites that are effectively types of site that we will consider when we study quantum magnets and Kondo systems. Okay, good. So let us now focus on a specific type of quantum many-body Hamiltonian. So we are going to have a quantum many-body Hamiltonian that has kinetic energy. This is a single particle term that we have been describing before, and then some generic type of interaction. Interactions are, in general, biquadratic interactions, and you can have all different types of combinations of the elements I, J, K, L. Afterwards, we are going to focus on some concrete ones, but in general, this is the problem that we need to solve. Even though this is a relatively simple problem to write, it is an exceptionally hard problem to solve. But what is interesting is that in very specific cases, we can actually systematically get solutions by using something that is called mean field theory. And in particular, this mean field theory allows us to predict a wide variety of symmetry broken states. In particular, we can predict the existence of magnetism if we have a certain type of interaction. So a magnetic system is a system where all the spins point in the same direction, meaning that we have spin up everywhere. And magnetism, for example, appears when we consider that the many-body interaction that we have in the system is a Hubbard interaction. So it's an interaction between spin up and spin down in the same side. Another type of correlated state that we can have is a charge density wave. A charge density wave is a state where you have electrons on one side but no electrons on the other side. And this reorganization of the charge has been driven by electronic repulsion. Electronic repulsion pushes all the electrons to one side but not to the other. And this type of correlated state appears, for example, if you have repulsion between nearest neighbor sites. So this is, again, a biquadratic interaction, but it's a biquadratic interaction not in the same site, but between sites that are nearby. Okay, so we have been discussing before that with second quantization, we are capable of dealing with these two different classes of Hamiltonians. We can deal with single particle Hamiltonians, and for these types of Hamiltonians, we can just exactly diagonalize the Hamiltonian, obtain the eigenenergies, and compute all the observables that we need. And in the case of many-body Hamiltonians, this is no longer a possibility, and we need to use some other tricks. We can use mean field theory that we are going to describe later on, but in some cases we need to use something else. And there are some quantum materials for which we need very specific techniques to understand their correlated state, and some of the specific examples are fractional quantum Hall states, correlated superconductors, and quantum magnets. But what is most important is that with second quantization, we can deal simultaneously with all these cases. So second quantization is going to be one of the most important tools in the course. Okay, so let us now start with a single particle system. And the single particle system that we are going to consider is just a tie-bonding model that from now on we are going to write in this second quantization formalism. So we have Tij, so T are the hoppings between site ij, then we have creation inside A, annihilation inside J. And then there's a certain geometry associated to these different sides. And for example, we can consider that we have a honeycomb lattice made in a finite geometry. So we can try to make, for example, a hexagonal island or a triangular island or a rectangular island and so forth. And since this is a single particle Hamiltonian, we can diagonalize it. And when we diagonalize it, we obtain the eigenvalues and the eigenvectors. And we can look at what is the probability of electrons to be at the different energies. We can look at each specific energy where we have an eigenvalue and plot what is the eigenvector in real space. This is what one can measure with STM, for example. And let us look at how it looks for different graphene islands. So if you take one of these triangular islands and look at what is the spatial distribution of your state at different energies, what you actually see is that you get kind of particle in a box state. So for the lowest energy, you get something that has kind of the strongest amplitude close to the center. Then you have something with more nodes, something with more nodes. Again, stronger amplitude in the center, but some nodes nearby, and so forth. So in practice, you can think that the single particle solutions of these tie-bonding models and of these single particle models, they naturally account for some of the things that you know from particle in a box physics. And they are in particular a finite size approximation to particle in a box physics. And this, of course, can be used for any geometry that you want. Before, you were seeing it for a triangular geometry, but you can see it here for an hexagonal geometry, and a very similar phenomenology happens. This type of profile is not just a result of a calculation, but it's something that can be observed experimentally using atomically resolved spectroscopy, in particular with scanning tunneling microscopy. And so many of the different observables that we can compute using second quantization is something that can be directly compared with the experiment. And in particular, many times, in order to rationalize what is observed in quantum materials, one needs to figure out what is the right Hamiltonian and the right many-body interactions to consider. And this is something that we are also going to see more in detail throughout the course. How we can see signatures of different types of contributions to the quantum many-body Hamiltonian in different observables. And of course, you can keep doing this for arbitrary arbitrary shapes of the system, including some rectangular shapes. Okay, so all those calculations that you saw before is not only something that you will see throughout the recordings, but it's also something that you can try by yourself. So we are going to use two important tools throughout the course to compute by ourselves all these different properties of quantum materials. One is Spicula, which is a Python library that effectively allows you to solve all different types of tie-bonding models, include quantum many-body interactions, obtain what is the symmetry broken state, compute topological properties, spectral functions, and many others. This is a very good library if you want to do some complex calculations in a relatively easy way. This Python library, and you will have Jupyter notebooks to try out all the different phenomenologies in quantum materials. And then you have also another library that has a user interface that it's called Quantum Lattice, that it's based on Picula, but that it has the advantage that you don't have to code at all. You don't have to write any Python code. You don't have to execute any Jupyter notebook, but you can actually just compute all the properties by clicking buttons and defining your Hamiltonian. And then once you are satisfied with your Hamiltonian, you compute the different observables that you wish. Both these two libraries are, of course, open source, and you can use them for anything else that you wish. Okay, so now let us look at interactions and mean field. So before we were discussing that we can use mean field theory to understand some of the correlated states. What we are going to do now is to do it explicitly. So in general, this is the Hamiltonian that we are going to consider. We have some free part of the Hamiltonian. This is a single particle term that we can exactly solve. And then there is some quantum many-body interaction that in general, it is a biquadratic interaction. A very important question is which form does the interaction have? And for our purpose, it can have many different forms. Of course, there's a contribution to this biquadratic interaction that comes from electrostatic repulsive interactions. It comes simply from the fact that electrons have charge, and charges of the same sign have repulsion. But you can also have other contributions to this interaction. In particular, if you have a quantum material that has also other quasi-particles around, like phonons or magnons or plasmons, then you can have effectively additional interactions that take this form. And in particular, you can have interactions that would not be allowed by only electrostatic interaction. You can have interactions that are effectively attractive. For example, if they are mediated by other quasi-particles. So in practice, we can have repulsive interactions, we can have attractive interactions, and many other things in between. For our purpose, we are going to just take these interactions as something that is given, We are going to work with some called effective models, and we are going to see which different phenomenology we can obtain just depending on what is the mathematical form of these interactions. Okay, and in the following, we are going to consider three different cases. We are going to consider the case of broken time-reversal symmetry, which is the case of magnets. So in magnets, we actually have a ground state that breaks time reversal symmetry, meaning that if you somehow record your system and play the movie backwards, then the system would be the opposite of what it is. Then in the case of broken crystal symmetry, we are going to consider charge density waves. So you have a system that originally it's the same in space, but once you consider many body interactions, suddenly it becomes inequivalent in space. So charge appears on some sides, but it doesn't appear on others. And the most sophisticated case that we are going to discuss today is a case of broken gauge symmetry, which is what effectively happens in superconductors. So in practice, in a superconductor, what happens is that there's an order parameter that is the superconducting order that has a phase, and the existence of this superconducting order effectively breaks a mathematical symmetry that the Hamiltonian originally has that is related with the symmetry when you do a gauge transformation. Okay, so let us start with the simplest case, which is the case of a charge density wave. And for this, we are going to consider a spinless interacting Hamiltonian. So in practice, we have a one-dimensional chain where we consider that we have hopping between the nearest neighbor sites, and then we have Coulomb interaction or nearest neighbor repulsion between nearest neighbors. And what we are asking ourselves is, what is the ground state of this Hamiltonian? If you just look at this Hamiltonian, all the sites are equivalent, right? So site number 1 is the same as site number 0, and so forth, if we consider that this is an infinite system. So the system has perfect translational symmetry. In order to solve that type of Hamiltonian, what we are going to use is mean field theory. And mean field theory relies on a relatively simple idea, which is the following. The problematic term in the Hamiltonian, or the challenging term, is the biquadratic term. So it's the term that has C dagger n, Cn, C dagger n plus 1, Cn plus 1. One way of approximating this term is by taking expectation values in between some of the creation and annihilation operators. So biquadratic interactions are hard, but bilinear are easy. So what we are going to do is we are going to take expectation values of 2 of the terms and leave the other 2 free. Leave the other 2 as if they were not affected by this expectation value. This is, of course, in principle, an uncontrolled approximation. There are, let's say, much more controlled ways of doing it using, let's say, a path integral and fixed point. But from a practical point of view, mean field theory just relies on this type of approximation. What matters is that once you make this approximation, then your system becomes effectively a single particle system. And in particular, this interaction term that was associated to density interactions between nearest neighbors becomes just an on-site energy, a single particle on-site energy. But what is most important is that this single particle on-site energy can be spatially dependent. There's no reason why this expectation value needs to be the same in all the sites of the system, even though the original Hamiltonian was translationally symmetric. When the expectation value is different in different sites, then you effectively have a charge density wave. You effectively break the original symmetry of the Hamiltonian. Now, an important question is, well, how do you get those expectation values? The way to do this is just by solving a self-consistent problem. And the idea is very simple. You can actually phrase mean field theory in a much more strict way, which is by saying that you are going to look for ground states that are product states in single particle basis. So you are going to look for the variational state that minimizes the energy and that it can be written as a product state of single particle states. So all these psi dagger alpha are just specific combinations of single particle states, and you are going to minimize the ground state with respect to the single particle states. So the way you do this is you compute the bracket between this ground state, the Hamiltonian, and the ground state again. Since this is a variational problem, what you want to do is to minimize the energy with respect to the single particle state that is parameterized by this chi. And in practice, what this actually means is that you want to minimize the energy with respect to the expectation value C dagger I, Cj, because that's of course what parameterizes your Hamiltonian. Now, this is a self-consistent problem in a sense that your Hamiltonian depends on the expectation values, but your expectation values require the Hamiltonian to be computed, right? So the way in which one can actually solve this is by making an initial guess to the mean field Hamiltonian. Then this initial guess allows you to compute a certain set of expectation values. With this set of expectation values, you can define a new mean field Hamiltonian. This new mean field Hamiltonian allows you to compute a new set of expectation values, and so forth. And the hope is that once you do this a large enough amount of times, or an infinite number of times, then you are going to converge to one solution, and this solution is the self-consistent solution of your mean field Hamiltonian. And so let us look at how this actually looks like for our one-dimensional chain with nearest neighbor repulsion. So this plot shows the single particle energy, the single particle energies of the effective single particle problem. So let us remind ourselves that we have a mean field Hamiltonian, and the mean field Hamiltonian is effectively a single particle Hamiltonian. And the x-axis here is the strength of the electronic repulsion. So at zero electronic repulsion, you effectively have a metal, so there's no gap anywhere. And as you ramp up the repulsion, suddenly a gap opens up in your single particle spectra. And this is, of course, something that you can see more easily if you look at the density of states, which in practice is just a histogram of the single particle states. So what you actually observe is that at zero repulsion, the system does not have a gap at all. And as you ramp up the repulsion, the gap opens up. And of course, the bigger the repulsion, the bigger the gap. So mean field theory allows you to account for the appearance of a gap driven by strong electronic repulsion. And this gap is actually associated to a breaking of the translational symmetry, to the rearrangement of charge, where charge goes to the even sides and it disappears from the odd sides, or vice versa. So in practice, if you look at this imbalance between charge, so if you look at the difference in charge between the even sides and the odd sides, what you actually see is that at zero interaction, the charge is the same. You have a single particle system that does not break translational symmetry, and as you increase the interactions, then the difference between even sides and odd sides becomes bigger and bigger and bigger, and eventually at very large interactions, all the electrons are in the even sides but not on the odd sides, or vice versa. Okay, so that was charge density waves. Let us now move on to magnets, and in particular to a relatively simple type of magnet that can be captured by something called a Hubbard Hamiltonian. So now the basic idea is that we are going to consider a Hamiltonian that has kinetic energy, but now we are going to have a spin degree of freedom. Hoppings are the same between spin up and spin down. And now the electronic repulsion is going to be an on-site repulsion, an on-site interaction between sides within the site I, but spin up and spin down. Something very interesting about this Hamiltonian is that by just changing the sign of your interaction, you can actually completely change what is the nature of your correlated state. So in particular, if you choose U smaller than 0 in this Hamiltonian, you can automatically get superconductivity, whereas if you take U bigger than 0, you get magnetism. U bigger than 0 means repulsive interaction, U smaller than 0 means attractive interaction. In our case, let us focus on U bigger than 0 first, and then we will go to the case of U smaller than 0. The way we solve this Hamiltonian is very similar to the one that we used before. So we identify that the problematic term in the Hamiltonian is the term that has biquadratic interactions. This is the challenging term that makes our problem exponentially hard. And what we do is we take expectation values between two of the field operators. And so when we do this, we end up with a bilinear Hamiltonian. And in particular, if we take expectation values between the C dagger up and C up, what we actually get is that the single particle Hamiltonian contains C dagger down, C down, and then the other combination would be C dagger up, C up. And in practice, this transforms the biquadratic Hamiltonian onto a bilinear Hamiltonian where we have a different coefficient for C dagger up, C up than for C dagger down, C down. And so in practice, what characterizes our magnetic order is the difference between these two expectation values, the difference between the expectation values C dagger up, C up, and C dagger down, C down. If this difference is zero, then we have a non-magnetic system. But when this difference is different from zero, then we have magnetism. And the way we solve this problem again is by using this idea of self-consistency. And what you actually can see is that if you perform this self-consistency with u bigger than zero, you get to a non-trivial solution, meaning a finite value of m. Whereas if you take u smaller than zero, then m is automatically zero. Now it is interesting to look at what is the symmetry that the magnet breaks. Time reversal symmetry is a symmetry that was originally present in the Hamiltonian. Time reversal symmetry is just the symmetry that switches the arrow of time. So if you initially go to plus time, you apply time reversal symmetry and you go to minus time. In particular, it also reverses the sign of the different angular momenta and the spin. That is a very specific type of angular momenta. If you now think in terms of the Fermionic operators that we have in the Hamiltonian, then time reversal symmetry effectively switches up spin to down spin. So terms in the Hamiltonian that were C dagger up, C up, they become C dagger down, C down, and terms that were C dagger down, C down, they become C dagger up, C up. And so in particular, if you look at what is the expectation value that characterized a magnet, what you actually observe is that if the magnetization is non-zero, then your system breaks time reversal symmetry, because when you apply time reversal symmetry to your magnetization, you effectively change its sign. And so a magnet is a system that breaks spontaneously time reversal symmetry. Time reversal symmetry is a discrete symmetry, and you can actually phrase a magnet as a system that breaks a continuous symmetry, which is this rotational symmetry, the rotational symmetry in the spin sector. And this breaking of rotational symmetry in the spin sector is what gives rise to the emergence of gapless excitations in magnets that are called magnons, that we will discuss in more detail in some of the next sessions. And so if you now take a minimal Hamiltonian for a magnet, what you actually observe is that the existence of electron-electron repulsion, if this is spinful model, give rise to a gap opening, and now this gap opening is associated to the breaking of time reversal symmetry. So what we are going to do is we take a one-dimensional tie-binding chain, and we take our on-site Coulomb repulsion, on-site repulsion between spin up and spin down, and as you ramp up the value of the Hubbard interaction, you observe that the gap opens up in the electronic spectra, and if you plot the density of states, you see that a gap opens up in the density of state. In the regime of very large U, this gap over here is what is called a Mott gap. It's a gap that appears due to repulsion in a spinful system, and it's associated to the emergence of a local moment in each site. And of course, this gap becomes linearly proportional to the interaction at very large values of the interaction. And then the last case that we are going to consider is the case of superconductivity. Superconductivity can automatically appear from the Hubbard model if you consider attractive interactions. And superconductivity is rationalized by one very specific contraction in the mean field approximation. So when we were considering this biquadratic interaction that had two creation and two annihilation operators, we actually should also consider that we can take expectation value between two creation operators or two annihilation operators. When we actually do this, we end up with a term in the Hamiltonian that looks quite different from the other terms that we had. So it's a term that it's not creation annihilation, but that it has two annihilation operators or two creation operators. This is a perfectly valid term in a mean field Hamiltonian. If you have repulsive interactions, typically the self-consistent value that you get is always zero. But if you have attractive interactions, like in the case of u smaller than zero, then you can get a non-zero value of delta when you do the self-consistency. And this delta is what we call the superconducting order. Something very important of this superconducting order is that it breaks something called gauge symmetry. And gauge symmetry is associated to the notion of the complex phase of a wave function or the complex phase of our field operators. And so from quantum mechanics, we usually think that the phase of a wave function is not necessarily physical, and the only thing that is physical is difference in phases. And this notion essentially tells us that we can make transformations in the phases of our wave functions and all the observables should remain the same. And if we phrase this in terms of field operators, a gauge transformation is just a transformation where we change the phase of our field operator. So the annihilation operator picks a phase e to the I phi, and the creation operator picks a phase e to the minus I phi. So if you have a term in the Hamiltonian that is C dagger C, regardless of the different indexes that you have, then the gauge transformation does not create any change in the term in the Hamiltonian. But if you have a term in the Hamiltonian that has two creation or two annihilation operators, then that term changes when you make a gauge transformation. And so since a superconductor has a finite expectation value of C dagger I, then a superconductor breaks gauge symmetry, and associated with this break of gauge symmetry, we actually have an associated fluctuating number of electrons. So gauge symmetry is also very much related with the particle number conservation. And so to summarize, I would like to ask you that you just remember the following points. That quantum materials realize a wide variety of exotic phenomena, that with second quantization we can rationalize both single particle systems and quantum many-body systems, and finally that mean field theory allows us to rationalize a variety of unconventional states, and in particular symmetry-broken states such as magnetism, charge density wave, and superconductivity.